Hi. This is my short presentation on my project pair production to the absorption of 2.2 megaelectron-volt photons in magnetospheres of X-ray pulsars. And just a little background on me and my project. I worked on this project this summer and fall of 2024 under the mentorship of Dr. Alexander Mushtakov. Um, and I'm currently a rising high school senior, though I've gone to college a year early, so I'll be a freshman in college um, this year. So my project is about these things called X-ray pulsars. X-ray pulsars are this thing called a binary system, which is where you would have a star and a neutron star. A neutron star is this star that's extremely dense and extremely massive. It's basically like one thing short of a black hole. And an X-ray pulsar is a binary system where this companion star, which is, even though it's bigger, it's much less massive than the neutron star, orbits around it, and they do something called accretion, where if you can kind of see the illustration here, which is by Dr. Mushtakov, by the way, um, you can see that kind of there's mass that's being sucked in by the neutron star from the initial companion star, you would call it. So this is called an accreting system, and this is part of what I studied in this paper. Um, these are very common. And because of this accretion, a lot of the mass hits the surface, and this causes it to emit a lot of photons, including X-ray photons. And so it's kind of part of why it's called X-ray pulsars. So my project was on this quantum electrodynamic process called pair production. So firstly, um, in this paper, we kind of focused on this energy band called 2.2 megaelectron volt photons. Megaelectron volts, if you don't know, is a unit of energy. So that would be the frequency of the photon, how energetic it is, how fast it vibrates, right? Um, and so it's a very high energy, and it's emitted through these things called hotspots, which are places where the accreting mass from the companion star hits the neutron star. Um, and so this particular energy band, 2.2 megaelectron volts, is emitted from this thing called the spallation process of helium-4, which is helium with two neutrons and, of course, two protons. And because it collides with incoming free-falling particles like protons, what happens is it would emit a 2.2 megaelectron volt gamma ray photon. And that's kind of what we focus on here. So now, a lot of stuff can happen to these gamma ray photons when they're emitted from the atmosphere. But the process we focused on here in my paper is a thing called pair production. So I have two processes here, one photon and two photon pair production. So in these things are called Feynman diagrams, named after Richard Feynman. I'm sure you guys probably know who he is. So um, this squiggly line here is a photon, and time axis would be left to right. And this photon on the left splits into a positron and an electron, where a positron is just a negatively charged electron, so it's antimatter. And so when you have these magnetic fields of X-ray pulsars, which are extremely strong, this is created partially by the mass itself and partially by the charges that are created by the accretion. So um, under these extremely strong magnetic fields and high photon energies, it has to be about 1 megaelectron volt or stronger, and you have to have a strong magnetic field. You can have a photon, like you can see here, split into an electron and a positron. And so what happens is this thing called the rest mass energy, the energy that's required to convert the energy of the photon to the mass of electron and positron is about 1 megaelectron volt. So you kind of have extra energy here. Um, and this can't work under no magnetic field, simply because the idea is that momentum conservation is not, it doesn't work, so it's not conserved unless there's a magnetic field to soak up the momentum that is created in this process. And then the one on the right you see is called two photon pair creation. And here, same thing kind of happens, except you have two photons collide and create pairs instead of just one photon. Um, And so in this paper, we did work on both one and two photon pair creation, but primarily focused on one photons, just because it's a lot more common. Because it's less likely for two photons to collide, and we kind of, for reasons I'm going to go into here, kind of determined that one photon creation is much dominant and more important. And we also use a thing called the dipole magnetic field model, which is just a model of the magnetic field of the electric pulsar that's very simple, just has two poles. Um, so essentially, the paper was simulating and deriving, but mostly simulating these processes and seeing how photons escape and what happens to them with regards to this pair production process when they're in the trajectory they're emitted from the X-ray pulsar. So, firstly, these pulsars are extremely massive, and mass bends time, you could say, and light is bent by this according to general relativity. So we use this thing called the Schwarzschild metric, which is essentially like a very oversimplified model of general relativity, which assumes the neutron star is not spinning and that it's a point mass in its very center. But using this, what we could do is this is not a new finding, but we were able to simulate the trajectory of the photon um, that's being bent by the gravitational field. Sorry. So if you can see like the figure on the right here, what you see is like there's a there's a neutron star, and so the lines are each line is photons emitted from a particular angle. So the right one would be pi over 2 with regards to the surface. Other would be pi over 4 and it would be pi over 3. And what you can see is obviously like the more perpendicularly it is emitted, the less it curves because it spends less time closer to the neutron star. And also each of these different lines, like the black, the dashed red, and the dotted blue, are different neutron star masses. And so the more massive it is, the more it curves, right? This is pretty intuitive. And what we kind of did is, what we have to do is simulate these trajectories, and on each point in the trajectory, calculate this thing called the absorption coefficient, which is like the cross section of the probability kind of um, the absorption. So what it actually is would be the inverse of the mean free path, where the mean free path is the average distance the photon would go without being absorbed. And so it would be the inverse of that. This thing is called the absorption coefficient on the left. So this graph on the left is just about how the coefficient works. When there's no mass, it's just a photon in a magnetic field. There's no like gravitational warping or anything like that. So you can see the black line and the um, red line. So they're for different energies, and the dashed ones are for a higher magnetic field. So as you can see, the absorption coefficient is very concentrated around when it's perpendicular to the magnetic field, because you see the angle and the absorption coefficient are plotted here. And so what you want is the coefficient is the highest, the more perpendicular to the magnetic field it is. And it kind of makes sense because the magnetic field is stronger. It's meant on like it doesn't work perpendicularly. Um and right, so what we can kind of see here is when the angle goes to 0 or to 180 degrees, it drops off to 0, the absorption coefficient. And so once again, what we did is we got this absorption coefficient. We did this approximation from a paper from 1988. Um, and we calculated the trajectories and we simulated them um, to get this stuff. Um, so first, I just want to say we use a lot of graphs. These aren't all of them. And some of these are actually graphs that I generated earlier on in the paper and then decided to scrap. Like the one on the right we used, but the one on the left we didn't use. Um, but I decided they were kind of good for the purpose of this presentation. So on the left, you can kind of see the absorption coefficient. So this is plotted against um, phi, which is the angle along the trajectory. So it's different than just the angle because now you would parameterize the trajectory of the photon, which is curved by the gravitational field by um, by the angle. Um, so what we can kind of see is as the photon gets further and further on the trajectory, the absorption coefficient drops off rapidly. And of course, we have two different magnetic fields, so you can see that like a slight change in magnetic field by approximately, well, not slight, but approximately by 0.25 times 10 to the power of 12 Gauss, which is units of magnetic field. There's a huge decrease in magnetic field strength, sorry, absorption coefficient. And you kind of see that like the vast majority of the absorption is concentrated within 0.10 radians of the initial trajectory, which tells us that the absorption happens at the very, very, very start of the trajectory. So like after it goes a little bit, it's the photon propagates for like less than like a millisecond. All the absorption is done because magnetic field is proportional to r squared or 1 over r squared. So Emir's square law. You can kind of see the same thing on the right here, where now you have the top one is the magnetic field strength. The one below that is the trajectories for different initial angles. Once again, that's the angle that is emitted from relative to the surface. Okay, I'm running out of time, so I'll go a little faster here. Right, and
No,
so you can
you're okay. Take your time. You have
okay,
time.
cool. You can kind of see the that once again on the one left here, it's logarithmic on the y-axis, but the vast majority of absorption occurs at very, very small distances from the center. And also, we also simulated this thing called redshift, gravitational redshift, which is just due to general relativity, you would have the frequency of these photons um, shift, to be more red essentially, so it would be slower. Um, and this would, of course, affect the energy because frequency is directly proportional to energy by Planck's constant. But we kind of noticed here that the difference in redshifted and non-redshifted is so small because redshifting takes a long time to happen. Like it depends on the distance, whereas all the absorption occurs at the very start. So we kind of determined that redshift was kind of irrelevant to these calculations. And so this big finding is called escape fraction. Um, so there's to the same graph. So on the left, it kind of shows the escape fraction. Escape fraction is where you would what you do is this would be the inverse of that. So it is the x-axis is the initial angle and the y-axis is the escape fraction. So it says what percent of the photons that are emitted um kind of, I guess you would say, how many of them escape. So you can kind of see here, um this will be the inverse of that actually. So the one minus the escape fraction with the probability of escaping. So you kind of see here is for initial angles that are small, you get um it gets absorbed instantly. Like every single photon that's emitted is absorbed. And then when you shift the angle by 10 degrees, 20 degrees, 30 degrees, depending on the magnetic field strength, and of course it's all for 2.2 electron volt photons, which you're focusing on because they're important. They're a byproduct of these deuterium formation reaction, which is discretized, which means you get this one energy all the time. Um, so you see that like for even for lower and lower magnetic field strengths, you have photons escaping really quick in within most reasonable initial angles. And once again, on the right, this is my favorite graph. It's the distribution, so like the probability distribution of photons escaping based on distance. And you kind of see like within 10 to the power centimeters, which is like that's tiny, it's like 10 meters tops, right? You have all of these photons all escaping. And also you see the probability of escaping kind of going to zero afterwards, and the absorption coefficient also goes to zero. And on top here, if you're interested, is the kind of way we calculate that, where tau would be this thing called um, it would be the integral of the escape fraction, sorry, of the absorption coefficient over the trajectory, and then we just take the exponent of this that's negative to get the um, coefficient. So yeah, so we see that like the vast majority of photons don't escape after um, at an initial angle of less than about 60 degrees, depending on the magnetic field, and then after that they all escape. So we can also see that like it's really based upon the time it spends when it's close by the neutron star because everything happens there. It drops up really fast. Okay, so some shortcomings. Firstly, we use this dipole magnetic field, um, whereas which is a very simplified model, because that'd be too complicated to simulate otherwise. So in reality, neutron stars have really strong and really complicated magnetic fields with many, many poles in them, as you can see on the left. And so we kind of had to not do that, especially because it's not really known the specific features in the magnetic field that X-ray pulsars have. So it's anyone's guess, really. So we had to use the simplified model. Um, Same with the Schwarzschild metric. That assumes it's a point mass and it's not spinning. So it is spinning and it's a point mass. It's not a point mass, right? Even though it's very concentrated. Um, and so in reality, we know that it's more complicated than that, and we have different results. So it would kind of act as like an approximation. And same with this graph on the right. This is the absorption coefficient calculated directly, whereas I'll be using in the previous graphs with the smooth lines were approximations. Because what this is it's called Landau levels, where the energy levels of particles are discrete. Um, and so you can see like these big jumps in the absorption coefficient. That's kind of the same thing. Um, Whereas the approximation kind of just approximates this trajectory that the absorption coefficient is going in without the Landau levels, because it's a lot more mathematically simple. And so if we had a lot more compute, we could have computed using the actual absorption coefficient as opposed to the approximation, but it's not a big difference. And for the purposes of showing approximately where everything happens, paper is very useful. So here's the significance. So a paper was published, I believe, a month ago in the Journal of High Energy Astrophysics. And so our findings, the kind of the big one is that X-ray pulsars with surface fields less than 10 to the power 12 Gauss are largely transparent to 2.2 megaelectron gamma rays, while fields more than 3 times 10 to the power 12 Gauss lead to efficient absorption within few tens of centimeters. So absorb like that. So you kind of be able to tell in like non-X-ray pulsars, but like other stars, neutron stars like magnetars, which have way stronger magnetic fields, there's no way a single photon is escaping that from the surface because it just becomes a pair instantly. Whereas for non-accreting neutron stars or ones with really small magnetic fields, you kind of don't see any pair production. So this was kind of our main finding, and this pair production itself had been calculated, but not for neutron stars or X-ray pulsars. So that was kind of our big finding. So the problem with that is there haven't been any observations of gamma ray band telescopes that are looking into neutron stars. So, but according to Dr. Mushtigov, at least, um, they should be coming out in the next decade. And so the idea is that their findings could verify, the observation could verify these findings, which would of course be great because what this helps us, which is a level that I don't fully understand, but this helps us um, understand and better quantify these things called neutron star mass radius relations, which are, as you can probably guess, the proportional relations between the mass and the radius of a neutron star because we still don't understand what's going on inside of them. Um, and so, like, to some, we know the surface, but we don't know the inside, and we have a lot of uncertainty regarding their mass and their radius and how they can relate to each other. So, if we were able to um, confirm this data in like 10 years, we'd be able to understand X-ray pulsars much better. So that's my presentation. Uh, Questions? Anyone?
My question for you, so long, is what was the most interesting thing about your study? Was there anything like surprising that you weren't expecting to find, or any questions that you still had at the end of the study?
Um, that's a hard question. I mean, I think I found the whole thing very, very interesting. I guess I know there was so much like depth and uncertainty to a tiny niche question in neutron stars, I guess. Um, and the fact that we didn't really know anything about them, because I thought we knew more about them, whereas there's so much uncertainty and gaps in our knowledge of all of these kind of stellar objects. That was interesting to me, but also, yeah, but it was surprising how kind of fun it was for me. I thought it'd be a little bit more tedious, but it was very enjoyable.